Next here, though, we have a tech talk on exploring new R&D progress that will shape the future of AI. Our speaker is Chief Scientist for Software Engineering at IBM Research, where he leads the research and development program on embodied cognition. Please welcome Grady Booch. Hello, Grady.
Oh, thank you for having me. Amazingly, both Joseph and I have been coming to you from Maui, Hawaii. So it's actually very dark here, 3 a.m. So I wish I were in Amsterdam, and post-COVID, maybe one of these days I shall join you. It's awfully early in the morning here to talk about higher mathematics, but I'm going to do so for a moment. I remember when I was first learning about fast Fourier transforms, I was utterly transformed by it, if I can use the very bad pun. Because if you think about FFTs, they gave us a way to transform data that's in one domain, be it time or space, into its inverse and vice versa. So the results were, the same in a sense, but transformed in a different way of looking at that same amount of data. In a way, we can look at AI in the same fashion. Neural systems are Turing complete just as symbolic systems are, but clearly they give us different ways of expression. Now, my work these days is in embodied cognition. That's why you see, I'll move to the side, you see the various robots around me. I've got a number of them that I work with these days. And because we work with neural approaches, they give us new ways to build kinds of systems. By the way, as you see on the slide here, I'm very accessible. Feel free to email me, follow my Twitter feed. I always respond to any messages like that. But what distinguishes an AI system from one that's not is this is my litmus test. An AI system is one that reasons and one that learns. If you only have one of these, then it's not really AI in my view of the world. You got to have both of those. And by reasoning, I mean some degree of inductive, deductive, or abductive reasoning. In learning, meaning we either teach it or it can grow in its cognition, if you will, over time. Now, this is the basis of where all AI lives today. It's not where it's always lived, because some of the things we saw from the past we wouldn't today call AI very likely, because we've sort of cracked the algorithms behind them. But what I'd like to do in the next several minutes is to explore where I see the forces that are leading us to the next generation of AI. If you read the literature, if you're just a casual observer of what's happening here, then you may say, oh my goodness, foundational models such as Microsoft's Turing and what's happening with OpenAI, with GPT-3 and the like, this is where AI is all at. Well, that's a piece of it. To that end, I'd urge you to go read this most fascinating paper by a delightful woman from Dublin. I'm going to get her name pronounced wrong because I've only read it, but we follow each other on Twitter. Abeba Birham, Abeba Birhane. Go read the latest paper that she wrote with regards to large language models. Gary Marcus has written some similar things. But while a lot of effort has been placed in the area of foundational AI models, there's much more, and let's talk about that much more, if you will. Well, again, we're talking about neural systems. This is the SNARK, the very first artificial neuron, built, I believe, by Minsky and his team. Took them, what, 6 electron tubes to do this. Obviously, we've been able to shrink things down a bit. Now remember that the very idea of neurons as a basis of computation sprung up from some really interesting work in neuroscience, but what we treat as a neuron in an AI is just a whisper of what real neurons are. Most of the neural networks these days aren't spiking. We don't deal with the electromagnetic connections between them. We don't even deal with the modeling of glia cells. Again, what we have in artificial neural networks is just a whisper of real neurons. That's actually interesting and great, and points out one of the forces that's leading us to new models of AI, meaning neuroscientists are coming on the scene In fact, I'm engaged with such a project at IBM where we're studying the architecture of the brain, the microcircuits and cognitive patterns that we see there that the neuroscientists are discovering. Go study Jeff Hawkins' work at Numenta in that regard as well. And it's leading us to understand that there may be some really interesting architectures the brain has that we've not yet explored in our AI systems. There are delicious hints that there are some forms of the transformer architecture at work in the brain itself, but there are also some really enticing hints that there are some structures at a higher level that we haven't even begun to explore yet. So this is one area where we see some very fruitful research taking place. Now, keep in mind that the neuroscientist world has been successful in actually mapping the entire neural network of the common worm. Some less than 10,000 neurons living within this thing. And yet, despite all the warnings from Nick Bostrom, the world has not been overtaken by these devastating sentient earthworms. Point is, we know how to map them, but boy, we sure have not built virtual worms. So clearly there's something missing here. And that's, again, a great thing because it tells us where we need to start looking again. So that's great. Of course, we also know, and this brings us back to the neuroscience view of the world, this was a rotating image. So move your head back and forth to get the animation, but it's not showing up. That's cool. Remember that we really have only begun to map the brain itself. And this is also a fruitful area as we move to these larger structures. I've been, for just fun reading, reading this fascinating book called The Handbook of Digital Circuits. And it begins to identify some of the patterns we see within the brain itself. Now, here's the model whereby I sort of shape most of the research I see taking place. On the left-hand side, it's our imagination. My dear friend Rita King, who works at Science House in New York City, coined the term the imagination age. And in many ways, we're limited just by our imagination. On the right-hand side, we want to build real running systems that do things in the world. Indeed, as a software engineer, the most important thing we produce is raw running naked code. That's on the right side. So the question is, what separates us between those two? And this will then give you a sense as to where interesting work is going on in the field of artificial intelligence that tries to bridge between our imagination and turning that into reality. We'll start on the left-hand side, which is the laws of physics. Obviously, you can't compute faster than the speed of light, no matter how much you'd like to, one of the profound limitations. But on the other hand, and I'm about to say something that is remarkably controversial in many circles, but that's okay because I think I'm right. Consciousness is an exquisite consequence of the laws of physics. And I think that's what's so enticing about AI research, in that we believe, if one believes in science and the scientific process, that sentience may indeed be possible to some degree of understanding because there's nothing supernatural about it. I'm not a panpsychic, but I think it really does flow from just the basic laws of physics. Not to say we understand all the laws of physics, but hey, it's nothing supernatural in that regard. So a lot of the things you see on the left-hand side, this is where computer science plays a role. But everything to the right of that then is a domain of software engineering. What's happening on the physics side? Well, a lot of what's happening is you see people are building chips, and this is great. And there's a lot of interesting research in this space telling us that we can we build these neural networks. That's great, but we'd like to build platforms that run them efficiently. Running and training neural networks is incredibly expensive. If you look at just the cost to train GPT-3, these deca-million parameter models, it's not cheap. And it really helps you if you have a patron who's willing to write off $1 billion in development costs. That simplifies your research efforts. Not all of us have that by any means. But one of the things that's happening on the sort of physics end of it is we're understanding the workflows, we're understanding the necessary computational power to run these neural networks, so it's possible for us to build hardware that indeed run against them. And that's a great thing because lot of research taking place to reduce the energy costs of these systems. Another phenomena that's happening, again, sort of the level of physics, is the shift from the cloud to the edge. With devices such as we see here from NVIDIA, I don't know if you can see it in the background here, but I've got my own little cloud running Kubernetes of all things on top of four NVIDIA Jetson Nanos. It's my research cloud that I have available to me. But it's remarkable how much computational power lives in these devices. And that's leading others to consider what are the right architectures in moving from the cloud to the edge and vice versa, especially as we consider the physics of data. Remember, data has weight in a sense, it has inertia, and so I'd like to be able to compute as much of it I can on the edge. That's leading towards some really interesting work in building edge-based chips like this. Sort of the next level is, if you take it to sort of the logical conclusion, are the kinds of things we've been doing in a project in IBM, project called True North, which is actually trying to build artificial neurons in silicon itself. And indeed, in one of our experiments, they were able to build a package that had as many neurons as the human brain did in about the same size. Not as many synaptic connections, but we know that as we move to, very single-digit nanometer processes, we aren't going to get exactly where the brain is, but we're getting awfully closer. So interesting work in that space. Sort of again, moving from right to left, now we're dealing with the issue of algorithms. And this is where a tremendous amount of research is still taking place. And it's an exciting time for the AI world because there's so much activity here. Now, remember, let's compare and contrast. We're talking about computation in the symbolic world, thinking back to the FFT uh, model here. Same kind of transformations. I mean, it's basically Turing complete. We're looking at it from symbolic versus neural. Symbolic computation is optimized to deal with the calculation, manipulation, presentation, and decision making of lots and lots of data. It's a world in which we tend to build models and manipulate those models. In the world of AI, today it's largely pattern matching of signals on the edge. This is where classification takes place. Frankly, this is where even AlphaFold fits in. We look at a certain set of data, we make predictions based upon it, and it's mostly all about inductive reasoning. But it's not quite yet, and there's again whispers of interesting research here dealing with decision making, abductive reasoning, and especially causal reasoning. I'm especially enamored by some of the things going on with Judea Pearl and what he's trying to do in the area of algorithms for causal reasoning. And as he says, we sort of understand the technology behind it, but we haven't really brought it into the forefront. So great stuff happening here. And this is also more so the realm of the large language models that we see here. And the point being is there's more to happen in this space. So let's continue moving across to the right. Building algorithms is one thing. We see Hinton working on sort of next levels of neural networks beyond just regression, and the kinds of algorithms you see today with gradients, very simple kinds of things. Well, we didn't call them simple back then, but they look simple to us now, and dealing with some of the shortcomings we know of our existing neural networks. So there's interesting and enticing progress in that regard. But now we're in the realm of taking these things and turning them to real running systems. And this is where algorithms come in, or architectures come into play. And this is kind of exciting because we're beginning to see patterns pop up in this space. In many ways, the AI community is beginning to discover what the software engineering community has sort of learned in the last several decades. We're beginning to see a language of patterns for neural networks. Indeed, there's even some books out of this space, machine learning design patterns. The famous book that this is paralleling is the Gang of Four book on design patterns. And we're finding that there are some common architectural patterns that are appearing again and again. Indeed, it's the transformer pattern that forms the basis of many, if not most, of the foundational large language models. And I think that's a great thing, moving from BERT to transformers. This is a representation that the community has begun to discover architectures that just plain work. Not to say it's the only one, but it is indeed useful. Another observation is that whereas you see transformers sort of the heart of this, another architectural pattern that's popping up a lot is a pipeline. Indeed, this is what IBM's Watson Jeopardy used, a pipeline architecture moving from right to left, from left to right, sort of augmenting the things we learn along the way, various agents working on top of it. And so we're seeing the pipeline architecture pop up also in places such as GPT-3 and the like. There are hints of it within AlphaFold as well. In fact, the sort of next generation of that is taking pipeline architectures and getting them to work together in opportunistic ways. This is an architecture called Self that we've been working on with embodied cognition inside IBM. It basically takes us the older ideas of Minsky's Society of Mind together with Rod Brooks's ideas of subsumption architectures and also the old ideas of blackboards to make them work together. Another area where some interesting research is taking place in the AI space is as we move across even further to the right, the things that look distinctly non-technical, but as it turns out are very, very important relative to the engineering of these systems. And that's just how we build them. Andre of Tesla made the great observation that, when you're building AI systems, it is just software, a very different kind of software. And so the kinds of things that take place here are not unlike what we deal with old kinds of software. Configuration management, dealing with continuous integration, continuous deployment pipeline, patterns that I mentioned. And so we're beginning to see the explosion of tools in this space that allows us to take these algorithms, take these architectures, and bring them to reality. So interesting research there. And then sort of getting toward the end here, now we're dealing with the issue of bringing these systems to the real world. So a lot of where I see research taking place, yes, some cool things happening at the bottom dealing with algorithms. We're coming to a better understanding of these neural systems, but the presenting problem is, how do I take those systems and bring them into the real world? It's not just engineering an AI system, but how do I engineer a system that contains these kinds of things? Yep, indeed. Yep. And so this is where a lot of the pragmatic engineering takes place, that we're trying to bring these systems to the real world itself. So let me leave this with you then. I mean, this is a great time to be in this space because, this is what we do. Software is the invisible writing. It whispers the stories of possibility to our hardware, and you are the storytellers. So thank you all very much for having me.